Sup guys, before we begin coding, which we'll do in a couple of minutes, I will just take a few minutes and go through a little bit about what a firewall is and how this project is going to be structured. So in order to describe what a firewall is, we need to describe what a router is. So let's say we have a simple network consisting of two different segments. So we can say that this is an office network connected to one port of this hardware firewall or router this far. And then we have the internet connection on the other side. Like so. The purpose of this router is to take all the packets coming from this network and forward it to the internet, and same in the other direction, like so. That is basically how a router works. It will just forward all the packets between those two networks. But let's say we instead have a firewall. We still have this office network to the left, but this time we give it a name, and let's call this inside. That's a traditional name for this kind of network. And it's connected to the left portion of the firewall. And the firewall in this case is a hardware device, similar to a router in its physical design. But it can also be a Linux server, for instance. So a regular computer with several network cards. And that's the purpose of the program that we're going to write in this series. It will turn any computer into a hardware firewall. Alright, so let's say we have internet here on the right, and I will draw this as a cloud like this. And this will be our outside network. Okay, so the purpose in this case is still to take the packets and forward them to the internet from the office network. But in the other direction, it will block most of the packets, like so, except for connections that has been initialized from the office network. That will be saved in a state database. Inside of the firewall. So when the return packet comes back, it should also be let through. So that is the difference between those two types of devices. The router will allow all different packets, but the firewall will allow only some of them. And we will also have different security levels. So let's say, for instance, that this office network has a security level of 9. I will abbreviate this as sec level, and internet has 0. So basically this means how trusted is this network. And traffic can always go from a high number to a low, and the return traffic may go back, but traffic that originates from the internet in this case, or a lower security level network, it will be blocked by the firewall. So that is basically how it works. And now I'm going to talk a little bit about the project at hand. So the firewall that I intend to write is called birdcage. And it is divided in two totally different projects. There is birdcage core, which is the core firewall. That's the part of the firewall which will handle all the allowing and disallowing of different IP packets and all that stuff. And that is what we're going to focus on in this series. Then there is the other part, which is called birdcage-ui. And birdcage-ui is the user interface. And that is a command line user interface, similar to how Linux or Unix systems work. So the user will log in to birdcage-ui system, and then we will have communication between those two systems. But this will be a completely different project written in a completely different language. We will be focusing on the interesting, cool stuff with regards to the real firewall. I will, however, release the birdcage-ui source code as well. So that is basically how it works. Sup guys, welcome to today's show. So let's code a firewall, shall we? I have already started a little bit by creating a template consisting of 3 files. So I have a make file for compiling everything. I have basically an empty .c file. And then I have this .h file, which is based on my template from my bash bs system. You don't need to know anything about it. You can go to the repo and bash bs and templates, and then you can just look at this h file here, for instance. And I'm gonna do some slight changes. I'm gonna change the name of these. I'm gonna change the name of these macros. So this is gonna be 1, 2, 4, and 3 bytes each. And as you can see, I just have a couple of includes, a couple of type definitions, and then the macros for converting from and to these types. Okay, and I also have birdcage-utils, which is my library with a couple of utility functions. It's also available in the repo. And I created a project called birdcage core, but I am naming my binary firewall D, and that D stands for daemon, and that is a common convention when you create programs which runs in the background, like servers and stuff. So this will be called firewall D. That is why I named the files like that. And I'm going to change the C standard to C23 because I'm running the latest GCC version. I think it's 14 or something like that. But if you're running a slightly older version, you can do C2X instead, and there will not be a difference in the project. Alright, so how do you code a firewall? Well, I have never done anything remotely alike, and neither has anyone else, basically, except for Linus Torvalds, who wrote the Linux firewall. But this would be a different approach. This will be a completely userland ring 3 firewall. So it will basically sniff for network traffic and handle those packets. And if we want to allow it, we will allow it. And if we want to drop the packet, we will talk to the kernel and tell the kernel to drop it. But that functionality we're gonna code a little bit later. I want to start out by doing the communication with birdcage-ui, because as I mentioned, this is birdcage core, which is the core firewall. And then we have birdcage-ui, which is a completely different project in a completely different language even. So that's not something we're going to worry about in this series. We're going to code the real firewall, so to speak, not the user interface. But we still need to interact with this user interface. And we're going to do that through something called Unix domain sockets. And that's basically like a regular TCP or UDP network socket, only it communicates locally on the machine using files. And why Unix sockets? Well, since both of these tools will be installed on the same system, I think it's good to communicate locally using domain sockets. Plus, if we were to use network traffic for communication, say, then we would have to worry about handling those packets inside of the firewall and stuff like that. Now this will be completely separate. Alright, that's all you need to know for now. So how do we begin this rather ambitious project? Well, two things. Communication with the UI, as I said, and also the config file, because there will be a configuration which will be stored in memory in some data structure we need to define, but it will also be able to save it to a file. So if the server reboots or anything, it should still be there. And we need to parse that config file. And that also makes it easier with the communication with the UI, because when we edit stuff and when we need to tell the UI about the configuration, we can just put that into a temporary file somewhere and trigger a reload or something. Alright, so let's start by defining the data structure for the configuration. And let's see. The configuration will look something like this. And it's inspired by the Cisco ASA firewall, which is a hardware firewall. And this is going to be a software firewall, but it will turn your Linux server into a hardware firewall. So it's kind of a little bit of both. And we're going to have a couple of interfaces. So let's say we have two network interface cards on our server. Then we are going to have an interface which is called E0/0, That is the first interface, and the configuration will actually, the command will be interface, but it can be abbreviated as int. And then we will have a couple of configuration lines which are connected to this specific interface. So we can, for instance, have something like MAC address, and then, I don't know, something like this. And we're going to use this format. Windows, for instance, uses a different format where you have, well, it's the same characters, but it's a colon and groups of 2 instead of 4. But I think this is easier to read, so this is what we're going to use. Perhaps we will later on add some functionality to converse between them. And we will also have something like IP address, and then, I don't know, something like this. And I haven't yet decided if we're going to use this format with a /24, or if we're going to have a net mask like this. This is the more modern approach, so probably going to use that. Then we will also have an ability to shut down this port. And I want to be able to shut it down in 2 different levels. So I haven't quite settled yet on what the commands are going to be, but I think maybe layer 1 or layer 1 like this perhaps, shut down. And this will turn off the electricity to the wire. But we will also be able to shut it down on layer 3. And we could have layer 2 as well, but we don't want to overcomplicate things. The important thing is that we can shut down the IP network interface, and also the firewall functionality for that interface. And that is what this layer 3 shutdown will do. And if we don't want it to be shut down, we will have like this. But this will not be shown when we show the configuration, so it will just omit the line. Okay, so this is the regular IP configuration and stuff, but we will also have firewall specific things, and all interfaces will need to have 3 things configured before we can take it off the layer 3 shutdown mode. First of all, it needs to have a zone defined. So something like zone inside. And the zone is just a name for the interface. And we also need to have a security level. And I have gone over a lot of things in my head. First, I was into levels 0 to 100. That is what Cisco uses, but I don't want to be... We don't need that many levels. So then I was thinking 0 to 10, but that's difficult to save in an optimized kind of way. So I think we are going to use 1 hexadecimal digit. So it can be either 0, 1, 2, 3, all the way up to 9, or it can be A, B, C, D, E, F. So the A here basically means 10. And maybe the Fs should be reserved for management interfaces or something like that. So let's for now think of this as up to E. And finally, we need to have no, that's all. The IP address is the third. So we need to have an IP address, we need to have a zone name, and we need to have a security level. And then we can remove those no's. I mean, we can have those no's. So now the thing is active. So we will, when we start the firewall, we will check how many Ethernet interfaces we have on the system, and we'll create interface E00 and then E01 and all the way up to whatever how many network interface card they have. And why the 0? Well, this could either be used if we need to add like modules. So let's say we can have other types of interfaces perhaps with a different series, or we can have more interfaces that can be added on later on. Or a third option is this number is the number of the firewall. If we have several firewalls in a group, we might want to let this be on firewall number 2, interface number 2, for instance. Sorry. Okay, so that's the interface. We're going to have a couple of different other options as well. There are some options with regards to the user interface. For instance, we will have users that can log into the system, and that basically means log into the user interface. So we'll have something like user, Jonas, password, orange. And then we either have root at the end or nothing at the end. And root means that this user is an administrative user. And we will also have something called a root key. By the way, not password. We are going to use pins. So we'll log in with a username and a 4-digit PIN number. And why that? That must be insecure, right? Well, if we just log in regularly, we will not be able to do anything, basically. We will be able to check the status of the firewall and stuff like that. But in order to change the configuration or check some more important stuff, we need to log in as root. And we do that by using a root key, something like, let's see, something like this. And I'm not going to go over this in great detail because it has more to do with the user interface. But basically, this is being used as an encryption key. And we will have a specific client that we will use this in combination with the PIN number to be able to log in as root. But we still need to support this in the actual configuration. And there are a couple of other stuff with regards to the UI, but those are the two important things that has to do with logins. And then we have the third thing, which we also need to support from day one, so to speak, and that is access lists, access control lists. So we'll do something like access list 5 permit and then some network. And maybe we will have something like permit host, and then we have one IP address. So either a complete network or just one IP address. And then we can also do something like drop any. So it will work like this. When a packet comes into the network, it will go through these line by line. So if it hits this, then it will permit. If it does not hit this, but it hits this, it will permit. And if it doesn't hit any of these two, it will drop any of the other ones. And this is a numbered, so-called standard access control list. And this can be from 0 to 99. And then they can be used for different things. Perhaps different interfaces, so maybe we have something like, I think we will do this down here actually. So something like, I haven't decided on the command. In Cisco you do access group and then in this case the number of the access list and the direction, inbounds or outbound. And then interface E010. So we'll have something similar to this. And by the way, we should jump in a little bit here because this is not connected to this. And we will have some kind of ending command as well, so it knows that we are done with this interface and these are global directives. All right. So this is basically what we need to support. Then, of course, we will add a lot of different other stuff. But in order to have a working version of the firewall with at least some stuff, this needs to be supported. So let's use this as a template and try to create a data structure capturing as much of this as possible, or everything of this actually. And that will mean quite a lot of different things. So let's see how we should structure this. All of this needs to be basically in every part of the firewall. So let's put all of this stuff in here in firewall d.h, the main h file. Okay, so we need to have a data structure for interfaces. Let's start there. So we'll do struct s interface. And it's going to have a, let's see, it's gonna have 2 of these numbers right here. And are we going to support indefinitely many? Probably not. Let's say we support 8 interfaces, at least per module, but for now 8 in total, I guess. Yeah, let's do that. That means we need to have an 8-bit data structure for that. So let's create one of those. Let's do a type definition, and let's call this, well, first of all, it's going to be an unsigned char, because that is the smallest thing we can have at this point. And as you know, an unsigned char is let's see, I think I mixed up. I didn't mean an 8-bit data structure. I meant an unsigned char is 8-bit, but we're gonna have a smaller than that. But let's start with an unsigned char. And what should we call this? Maybe IF number for interface number. And let's see how much we need. I think it's a 3-bit structure, because let's see, if we have 0, 0, 0, 0, this to the right is 1, 2, 4, 8. And if we count the 0, we just need the 3. So 3 bits. Which means we'll do IF number, and let's call it ID, and we need 3 bits for it. And I think I have shown this syntax once or twice. Basically, you do a colon and you tell it how many bits we want, and that only works inside of a struct and similar structures. Okay, so that's the first. Perhaps we should mark that in some way. Let's see. Let's put 2 like this, so we know that we're done with that. Then we need to store a MAC address, and a MAC address is a 48-bit thing, which is right in the middle of all the different stuff, because we have an int 32 and we have an int 64, but we can't create an int 48 that way. So we need to use this same syntax. So let's do that. Let's type def unsigned. Maybe we should do like this instead. It's a little bit easier to read, I think. So we have int 8 for this, and we'll have an int 64 for this, and maybe even like so. And this will be a MAC address. And then we'll have MAC address MAC with 48 bits. And then we need to have an IP address, but not just an IP address, an IP network with both the IP address and this CIDR, as it's called, classless interdomain routing. But we will also need to have support for IP addresses, so let's create both. Let's type def int 32, and this will be an IP address. And let's see, we need to create a structure for the network. But first we need something for the CIDR as well. And CIDR goes from 0 to 32, but the 0 is rarely used on its own, so we can probably get away with, let's see, so we have 0, we have 1 and 2 and 4 and 8, we have 16, and we have 32. So we need 5 bits for the CIDR. So the thing that is closest to this, closest above, is int 8, and this will be a CIDR. And then we will do a struct s net or network, and this will contain an IP address IP and a CIDR. Size maybe. And let's type def struct s network to network. And then we can put in the network net, like so. And we have support for this line as well. Then we have those shutdown states that can just be a simple boolean. So let's do maybe we can do this. If we were to put in a anonymous struct here, and then we have a bool at layer 1, and we have a bool at layer 3, and then we just define these as shutdown. This way we will be able to reach these using, so if we have one of these and we call it int, we will go to int and then shutdown and then layer 3. All right. And this should be zone. And this will just be a regular string. We don't have to create its own data structure, I don't think. Nah. So we'll have an int 8 zone, Or maybe we should do it like this. Let's say we allow 16 bytes for this. And security level, there we will have 16 different combinations. So we have 1, 2, 4, 8, 16, so a 4-bit structure. By the way, these should be 1 bit each. And this should be 2 bits. I'm not sure if you can do that. We'll see. Where were we? Right, security level. I want to have one of these for that. Type def, and the closest is int 8. This will be level. Or maybe sec level. So we will have a sec level 4 bits. Alright, we're making fast headway here. Let's wait a little bit with this one. I want to put it on the bottom actually. So how do we represent these users? Well, it needs to be some structure with an int 8 as the username. And then we have to have a PIN number. Which goes how far? To 10,000. Let's do a small script. So let's see. For I in, and we'll do a sequence from 1 to, let's say, 16. At each location, we are going to echo the number to the power of 2. Is equal to then we take $I times 2. Done. And we need to add -e, I think. That's more like it. Okay. So let's see. But this doesn't look quite right, does it? 2 times 2 is 4. 3. Did I? Yes. I took the wrong order. It should be 2 to the power of this. This looks more like it. Alright, so we want to have something with about 10,000. And the closest thing above is this, so 14 bits. 14 bits for the pin number. Let's type that down so I don't forget it. And then we need to have a boolean if it's root or not. So let's type def. And let's see. What did I say? 14. So an int 16 should be the closest. And this is a pin code. And we will type, no, we will struct as user. We'll have an int 8 username. And let's say we have 16 as limit here as well. And then we'll have the pin, so pin code, pin 14 bits. And then a boolean for the root. So bool root 1 bit. This is a user struct type def struct as user. And we'll put it right here, user. I don't know if we can do this. I don't think so. Account, perhaps. Okay. And the root key. Let's see if I remember. This first thing goes from 0 to 1023. So so we need a 10 bit for that. And this goes from 500k to 1.5 million. Which means we need to run this a little bit longer. 1.5 million. 1, 2, 3. 1, 2, no. Here we have 1 million and 2 million. So 21. And it's not really necessary to be this kind of granular and optimized, but I like it to be pretty neat. So let's see, how do we define that root key? Well, the first part is the actual key, and the second is the number of the number of rounds. So let's call this, just so we don't get a conflict, we'll call this a subkey, which is not 100% accurate, but let's say it is. And the other thing should be not an int 8, but an int 32. This will be rounds. So let's create a structure for this. Struct s. Root key. And we will have a subkey type, and we'll call this the key. This will be 10-bit, and we will have a number of rounds. So let's call it n for n number of rounds, and this will be 21-bit. Typedef struct s root key as a root key. And we'll add this as a root key. Okay, we are almost done with this part. Fun as it is. And this is another story. No, it's not so difficult actually. Not at this point. It will be much more difficult when we allow for extended access list, but that will probably be in the next version. So for now, this is all we need, and we already have the network part. So we basically only need to add something for this action. And the number of the access list. So let's see, the action I think I want to define as an enum. And we're going to start with just two different actions. We will have a permit action, which is number 1, and we will have a drop action, which is number 2. But later on, we might increase these. So we will do type def enum e action. go from 0 to 99. So we have 1, 2, 4, 8, 16, 32, 64, 128. So 7 bits. So we'll do a structure for this, and let's call it standard access control list. And it has a number, so this will be an int 8. And what should we call this? This identifier, perhaps. Seven. And then we have the action, and I'm not really sure how big these are. Actually, let's find out. So if we create tmp.c, we paste this in. And let's just do this. Maybe we should have an include as well. And we'll print %d, and this will be size of enum e action. Four. So it uses an entire integer. Well, we're not going to do that for sure, but we're not just going to use 2 bits either, or 1 even, because we want to have room for a little bit more. So let's say we have 3 bits for this. So we'll have an action, act, 3 bits. And then there's just a network. So network, net, and then we type def struct s standard ACL, standard ACL. And we put it inside of here. And this needs to be an array. I suppose. Or a linked list. Let's see. We need to have several lines. And several ACLs. So maybe we could call this something else. Let's call this an ACE, an access control entry. So this is for just one. And then we probably don't need this identifier. So it's an action and this. And this is an ACE and an ACE. And then we can do something like type def. If we have std ACE 99. So 99, no, that's not it. That's the number of ACLs. But let's do the same. Let's say we have a maximum of 100 entries per ACL. I think that is reasonable. So 99 ACEs is an ACL. And then we need to have room for standard ACL. Let's just call this ACL for now. And we need to have 99 different ACLs. That's not very optimized though. If we don't only use one, we still have room for a lot of these. So it's good that we saved a couple of bits here and there, so we could waste them here. But I don't want to go the path of linked lists unless I need to. Maybe I can have this in the back of my head, and then we can. Then I can probably write this so it will be easy to change later on. So now we have support for all of these. And the any, by the way, will be the same as 0 IP address and 0 here. So we don't need to have any extra thing for that. And then we just need to enable it as well. And maybe the easiest way is just putting it inside of the interface data structure. Did we create one of those? Wait a second, we put everything on the interface here. That's not really what we want. Those 3 lines we want to put on its own. So let's create something for the ACLs. So we'll have an ACL or not. We might not have an ACL here. So maybe we'll do it as a pointer. So let's say an inbound ACL and outbound ACL. It's too long. ACL in, ACL out. So the number so we have the number, since we have a reference to an ACL with that number. We have the direction and it's linked to the interface. And if this is pointing to 0, then we don't have it activated. That's good. So these are all the different AC interface options. So we'll type def struct s interface as interface. And now we can create our final thing, which is the config. And here we will have a couple of interfaces. So interface, and how many did we say? 8, right? So if, we can name it if, because if is a keyword. iFace perhaps. And we need to have up to 8, so 7 here. Or let's make this pointer instead. Maybe even an array of pointers. Then we can allocate one at a time when we enumerate these interfaces. And that's pretty much it. I think. So we'll type def as config to config. So now we can keep the entire config in this structure and just pass it around to the different parts of the program. Or perhaps maybe even have a global variable or something. We'll see how this plays out. We can also pass it around as a self pointer, passing it as a reference to the functions that are going to need it. All right, we'll take a short break. What's up, guys? I'm going to take a few minutes and show you how this UI is supposed to be. So when you log in, it looks like this. This is a prompt where you can type and you can move through your different commands. So if, for instance, do show version to see the version, I can press up arrow and I can modify the command and I can cycle through all the other commands, exactly like a modern Linux prompt, but quite difficult to get right actually if you code it from scratch like I did. Alright, so you can also do, if you don't know the commands, you can, for instance, or maybe you know part of the command, you can do, let's say, show, and you press tab, and you get a list of the different possible commands. You can at any point also press question mark, and you get a more detailed list with a little bit of description for the different commands. But if I want to do show run, for instance, that's short for running config, to check the configuration, this command will fail because at the moment I'm logged in as a regular user and you need to be root for that to be possible. Same if you want to do like configure and stuff like that. Alright, so in order to elevate your privileges, you type elevate, and then you get one of these challenge numbers. So you copy those, and then you go to a different, let's see, a different window, and you run the BC login program, which looks like this. You can add a key for different firewalls, so you can have a list of those. I will not go through how that works with keys and stuff, but in my case I just type BC login firewall. It will ask me for the challenge and I paste in those numbers. It will ask me for a PIN code, which is personal to my user. So I enter 4 numbers, and now it encrypts this challenge with this PIN code and a so-called root key. And this is the result, 3819 in this case. And this is different every time. So 3819, I just type it in, and now you see that it's a hash symbol instead of this greater than symbol. This means that now I have access to all the commands, so I can do show run to check the configuration, for example. And at the moment there are not so many options. It's for the host name, it's this name right here, and I can change it by going into the configuration and just typing in host and then the name of the device, let's say router 5 or something. And as you can see, it instantly changes this prompt. And this is an example of a root key, and you can generate one of those by typing generate and then some random number, but I haven't yet implemented that feature. But the most important as of right now, in order to make this work together with what we're going to code today, I'm going to show you. Let's just first elevate, take those new numbers, and those are randomized, so different each time. And we do the same again. You only need to do this once per. Okay, I typed in the wrong pin number. You only need to do this once for every login you do. But since I got locked out, I need to do this again. Ta det lugnt nu, för så måste jag göra klart det här. Det är jätteviktigt. Alright, so let's see. Let's say I want to create an access list that's defining what IP addresses and so forth that should be allowed. So I just do access list, and we can do the question mark to see the syntax. So we give it a number, and we can permit, for instance, the network 10.1.0.0/16 and perhaps 192.168.10.1/24, and maybe we want to drop the IP address of 212.16.16.24 or 23. And then maybe we want to permit everything else. So permit any at the end. And if we do sh run access list, we see any commands with regard to access lists. We can also do just show access list without the run, and we will get this table describing the different parts of it. So in this case, we will allow these networks. No, we will allow these two networks, and we will drop this IP address and permit the rest. So that's basically how it works. Let's see if I forgot anything. Yeah, and here is how we can add a root key for authorization. And we can also add a user. So we say user and the username, and then pin and the pin code, and if we should allow root access or not from this user. And this is quite basic functionality this far, but there will be more features and more advanced access lists. But this is so we have something to work with. And you haven't missed any video, because this I have done on my own, and this will be a separate project. we will focus on the core firewall, which is the cool thing. So let's continue with the code. Sup guys, welcome back. So before the break we started out with our firewall project and defined different data types for the different parts of the configuration. And I did one thing after during the break, and I just selected this thing, the user account, so I wouldn't forget, because we don't just have one user account, right? We need to have several of these. So let's see how we can best do this. I don't really like the way we did with the access lists, that we created 100 of those in a array. We could do the same for the user accounts, but it's not really a good way to go. So what alternatives do we have? We could just make this a pointer and then allocate as many as we need. But I think we need to decide how to do this in a more general kind of way. Either we do like this, so we make it a pointer and then we allocate, and then we can reallocate when we need more, but that's not very effective. So a better solution is creating either a linked list, but that's also kind of slow. So I was thinking, what if we create a general type of a dynamic array. So a dynamic array has the following structure. Let's say we create something like this, and then we will have first of all a size of this thing. So let's say we have an int16 size, and then we need to have a capacity. So let's say we have an int16 capacity, and I wonder if int16 is the best. Yeah, it is. We're not gonna use more than 65k anyway. So basically the size is how many entries do we have in this list. The capacity is how many entries can we fit in this list. So let's say it by default allocates space for 50 entries. Then the size will be 0 from beginning, and the capacity will be 50. And when we reach that capacity, so the size is equal to 50, and we need to have more, then we will allocate an additional 50, and so on and so forth. And we need to have a third thing, and that is the actual data that we need to store in here. And since we want to make this a general type, which will be able to handle different kinds of structures, we have a couple of different possibilities, I suppose. But I think in this case, the easiest way would just be to make them void, and then have something of the sort let's see, let's call it data. And then we create a type definition for our structure as dynamic, and let's call this what if we were to call this just dynamic, I think. Alright, so we need to have something which creates one of those and handles the size and so forth and the allocations. So let's start with a constructor function, and we need to decide how many should we have. And since some of the structures might be kind of big, I think 20 or 10. Let's see. 10 access lists. Yeah, I think that's okay. So let's make a definition for that. Something like define and then din block size. It's too big. Let's just call this block size. Maybe we can have like this. So let's say block size is 10. And then we need to have a constructor function. So it will return a dynamic array pointer. Let's call it make dynamic. And what do we want to have in here? Nothing, I think, because we want to create an empty one, and then we want to have other functions as well, something which will, let's see, that will add something into one of these. So let's call it din add, and it will return the new thing. So din, or maybe not actually. Let's do it as a void. So din add, and it's going to take a dynamic array, and it's going to take an entry of type void star. So we can add to it, and we can create one. I don't think there's any point in deleting. Or is it? How would we delete something from it? We would have to create a new one and copy over stuff. I think it's better to just zero out in that case. I guess. Let me just think a little bit. Let's cross that river when we need to. So let's put this in code. So we need to create the constructor, make dynamic, no argument, and we need to have a pointer for this. And what do we need to do? We need to have a size as well, and the size should probably need to be an int32 in this case. And what is the size? Well, it will be that basically depends on let's see. Depends on how we're gonna store stuff inside of this. Do we want to store just a pointer to another allocation, or do we want to store the actual thing? Maybe we could actually store the actual thing. In that case, we would give it the size of that thing. So the size would be like this. Or okay, so let's see. We need to have a size. Maybe we could do this instead. We create a count. So the count is the number of things we have in it. The size is the size of each thing. The capacity is how many entries do we currently support, and the data is the actual data with all of these entries. I think that's the best solution, actually. Maybe we could even do it better. What if we were to call this dynamic prime? I'm going to show you why in a second. Alright, so now we will have this would be make dynamic prime, and this will be an int16 entry size. And then we have an int32 for the whole thing. And I want to make one small additional change. Instead of just doing void data like this, let's do int8 data and make it an empty sized array, which we can increase by doing the actual allocation. And why int8? Because then we can just copy the bytes into here. This is a rather elegant solution. I'm going to show you in just a sec. Alright, so how do we calculate the size? Let's do it in one step like this. So the size is going to be the size of the actual structure, so the struct S dynamic, and then we need to plus the entry size times the number of entries, which is our block size, because we want to create 10 of these from the beginning, or at least space for 10 of these. So now we have the size, then we can make the allocation. So P is going to be a dynamic, and we malloc size bytes, and we're also going to clean them out. So we will 0 our P and size bytes. Let's also assert that we have a P, because if the allocation fails, then something is seriously wrong and we should just quit, I think. And just to make stuff explicit, we can do like this. We can set the count to 0 like so, and we also need to set the capacity to the block size, which is 10 in this case. And what else do we have? We have the size of the whole thing, or the size of the data. So how much is that? That is the entry size times block size. So size is equal to entry size times block size. And then we just return P. And why did I call this make dynamic prime? Because now we can create a macro, a function-based macro, which we call make dynamic without the prime. And then we're not going to take the size of the thing, we're going to take the data type. So this will be something like, what is it called? Not a higher order function, but a higher kind of type, actually, or something of the like. So let's see. So if we have our definitions here, we can have our macros here, or we have macros somewhere, don't we? Yeah, here. No. Here. So let's create a macro for make dynamic. And we're going to take an X as an argument. And what are we going to do? We are going to call our make dynamic prime. And we're going to pass the size of X. So now we can call this function by doing something like, for instance, if we want to do it for a standard access list, we can create something like this, and we can do ACL is equal to make dynamic, and we give it the data type, standard ACL. And then it should create 10 of those. Kind of nifty, huh? Have you seen that in C before? I don't think so. Alright, so now I have created this thing. Next step is to add something to it. And are we still gonna use void here? Yeah, I guess that is the best way. So let's create void add, and what are we going to give it? We're going to give it a dynamic array. So dynamic R or R, and then we're going to give it the thing we're going to add. So entry. So how are we going to handle this? Well, let's we have two cases. Either we have space to add it and then we can simply add it, or we don't. So let's make a case first. If our arrays, let's see, if our arrays count is more or equal to, it should never be more, but who knows, better to do it like this. But if it's equal to the array's capacity, so we don't have room for this thing, then we need to increase the capacity. And we're going to increase it by block size, which means that we need to have a new size. Let's see. Let's also create something called n. So block size, entry size, and we need to know the new number or the new capacity. So the new capacity should be the old capacity plus block size. So we increase it by a block size. And let's set n equal to entry size times the new capacity. So this is our new size of the data portion. And we also need to have a new total size. Maybe we should use the size here instead, so we don't mix our different names for them. So this is the size of the data, and then we set n equal to the new size of the whole structure, which is the size of struct s dynamic plus the size of the data. And now we can make the new allocation, and we do that by saying we need a new pointer for that, I suppose. Or probably not. We can use R. So R is equal to dynamic, and then we use realloc to change the size of the allocation. And we give it the old pointer, and we give it the new size, which is n in this case, as an integer. Something like that. And we can once again assert that we have an R. So now we have successfully increased the size of this. We also need to update the capacity inside of the structure. So R capacity is equal to cap. Like so. And the rest won't change. So now that we have increased it or not, perhaps we had room as it was. By the way, let's see. All of these are int 16s. The capacity could be an int 16 and the count, but I think the size should be an int 32 because it could be quite big. But it is the size, wait a second, it's the size of the individual things. So let's do this. Oh, did I do now? Let's see, so I didn't mix up some stuff here. Size is entry size times cap. Let's set all to 32 instead. We don't really know at this point what we're going to use them for, so we need a lot of room. So cap is equal to the current capacity plus block size. That's a new cap. The size is equal to the to the entry size. The entry size is the R size times the capacity and then we just add the rest of the structure. We allocate, assert, and we update the capacity. Yeah, sounds good. Let's also, just so to make it clear, we create an index. Because the index, the new index of the new thing we are about to add, is going to be the old size. So it's the R count. That's what I meant. Because if we have 3 entries, the count will increase to 4. And if we want to access the 4th element, that will be 3, counting the 0. So the index should be 3. And now we need to copy in the new entry. And we can just do a memory copy. And we need to define what that means. So let's see. We're gonna copy it into the arrays data at the index. And we're going to copy from the entry. And how much are we going to copy? Well, it's the size of the individual thing. But we set the size to the entry size. Maybe it's better to call this entry size so we don't mix it up, as I have done multiple times already. So this is the entry size. And the entry size we get from this. And the entry size is equal to the entry size. I think this is the best way. Then we can just do like this. So we take the individual entry size and times it with the capacity. Do we do the same here? We take the entry size times the block size. And here we take the cap and we times it with the entry size. I think this is the right thing. So we memory copy this stuff, and then we can just return, I guess. But what is memory copy? We need to define that as well. So memory copy is going to be a void function, memory copy. It's going to take an int8 source, int8, destination, and an int8 source. And it's going to take an int32 as a size. So we have void memory copy int8 destination, int8 source, int32 size. And we need to have an int8 pointer. And we need to have some n for knowing when we're done. And then we do a for loop where we set p equal to, by the way, we can't just have a p, we need to have one per source and destination. So let's have a d and an s for destination and source. And we set d equal to destination, we set source s equal to source, we set n equal to size. And we're going to loop as long as we have an n. And what are we going to do at each iteration? When we're going to increase the destination and the source, and we're going to decrease the n. And then at each iteration, what are we going to do? We are going to set the destination equal to the source. And then we're going to return. So this will go through n number of times. So size number of times. And just copy 1 byte at a time. And let's also create a function that will print the contents in some way, or at least information about it. So let's say we have a void din print, and it just takes one of these dynamic things. There should be dynamic pointer there and there. And what will the print thing do? Well, din print, and it takes a dynamic R. And we will just print some information about it. So let's say I wonder if it would be beneficial to save the type as well. At least for the printing purposes. We could actually do that. So let's just say we have a small int8 type, and it shouldn't need to be bigger than 16, and if it is, we will only put the first 15 bytes of it there. And how can we put something in there? Well, we need to use our macro. We call make dynamic with the size, and let's also give the string representation, or rather the int8 representation of the string representation. And I always seem to forget how to do this, but I think we use this hash symbol like this, which means we need to add an argument to the make dynamic, and that is just a int8 pointer representing the string. That will be kinda cool to save the data type as well, or the name of the data type. So here we will have a int8 data type, and we are going to memory copy into the p type, and we take the data type and we simply copy, let's see, we can use the min function or the macro. So the thing, we give it 2 arguments, and the one that is the lowest will prevail. So let's say the first being the string length of the data type, and the second being 15. So that way we will not copy too much. And we need to define what min means. So we'll have a macro called min with an x and a y. And let's see, in case x is less than y, then we will return x, otherwise we'll return y. Yeah. Okay. So now we can do a kind of nifty print function where we are going to print let's see. Let's do data type. And then we'll have the name of the data type. And a new line. Let's jump out a little bit. And then we will have the capacity. Maybe we can just do this actually. Maybe we can do it even better. What if we were to do something like printing, and then we do this, and then we have a data type. Like so. And then we have the capacity. Entry size. And what else did we have here? So entry size, capacity, data type, count. So that's a number of things. And then we have data. Let's do this. Count. And entry size. And then we do a double like this. And the first should be the var. I'll come back to what that is. And then we will have the data type, which is the rs type. Then we have the capacity. And count. and the entry size, like so. And let's also add this var, which should be an int8 pointer. This should be the name of the variable. Alright. And then we show some of the data. Let's say we do a hex dump of the first, say, 32 bytes. So we do print hex, and let's see if I remember the argument list for this. We want to print the R data, and let's see. And we want to print the minimum of either the count times entry size, so we don't overflow this thing, or 32 if that's the lesser one, lesser or equal. I think that's good. And we also might have some kind of separator. Let's just do without. And then at the end, we just do an extra new line and return. Okay, so how can we get the var here? Well, we do the same trick as before. We call this dinprint prime. Dinprint prime, and we add an int8 pointer. And then up here, we define dinprint, and we just take one argument here, so we have an x, and we call dinprint prime, and we give this the x, but we do also give it the x, like so, like we did down here. And this $1, that's just a typecast from string to int8 in this case. Alright, kinda cool solution if you ask me. Let's see if it works. So, what do we need? We need to have a dynamic array. By the way, we need to assert that we have an array, and let's also assert that the array has a count. Which reminds me, we forgot to increase the count when we add things to it. Like so. So R should be equal to make dynamic, and what is the data type we want to add here? Let's say we add integers. So we just give it int, like so. Let's just see that I thought of this right. So make dynamic of x, size of, yeah, that should be it. So make dynamic int. So now we should have 10, we should have room for 10 integers. So let's add something to it. So din add, and we want to add to our array. And what do we want to add? Well, we want to add some numbers, right? 1, 2, 3, 4, 5, say. And then we run din print, and we give it the array, and then we free the array and return. Alright, so let's see if this works. We probably need to fix a couple of errors, but let's start. Define input of x is not followed by a macro parameter. Okay, it doesn't like the parentheses. So let's just remove those. Width of key exceeds its type. So how did we define the subkey? Subkey as an int 8, it should be in 16. Expected identifier, alright, line 93. I made the wrong syntax. So where do we put the 99? Do we put it here, perhaps? Bitfield shutdown has invalid type. 102. Maybe we can't do that. Can't define the bit length like that. Type def sconfig, config, unknown type name sconfig. Yes, that's right. Because where do we have config? Right. This should be struct as config. Let's see, memory copy, stringlen. We haven't defined the stringlen function. Let's do that as well. So we are going to have a void. No, not a void. Let's see. Let's do it in 16 in this case. So string len, and we would give this. Let's see how we use it. String len. We give it data type. We give it an int 8. So let's do that. Int 8 star. And how do we create a string length function? Well, it's pretty simple actually. Int 16 string length, and we give this an int 8 str. And what do we need? Well, we need an int 8 p, and we'll do a for loop where we set p is equal to, we need to have a counter as well. We set p equal to str, we set n equal to 0. We're gonna loop as long as we have a p, and we will increase p and we will increase n. And then we'll just return n. Cast pointer from integer different size. Memory copy $1 R data index. Dynamic has no member. Name size. No, that's not it. Cast pointer from integer R data IDX. It is the correct size, but it's an empty array which we have allocated for. Let's see how we did this. Memory copy int 8, int 8, int 8, int 8. This is equal to this. And how do we call it? Memory copy copy memory copy p type. And the type it's an int 8 like so. Is this the line it's complaining about? No, 53. So our data at IDX. Maybe we should do some pointer arithmetics instead. So let's see. If we have an int 8p, and we set p equal to our data, so that's the first one. And then we plus it by the R entry size times the index. And we put P here instead. That should be right, I think. Has no member named size, 55. Okay, so this should be the entry size. Expected blah 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 before printf 63. Did I forget a parenthesis perhaps? There we have this and this and this. Here is one. Here is one. And here's one. Ah, up here, okay. Maybe we don't need to assert that it has a count. Let's just do an if statement down here instead. So if R has a count, Then we do this. Let's see. In expansion, blah blah blah, make dynamic int. Incompatible type for argument 1 of din add. The R. Okay. What did we say that din add had for first argument? Dynamic R. Din add dynamic star. We forgot to make it a pointer. Okay, we're down to just one error basically. In expansion, blah blah blah, expected expression before this parenthesis. R is equal to make dynamic int. Size of int. Maybe we shouldn't put it in parentheses. Which was it? Make dynamic. Maybe we should just do that. Here though, we should do this. And why do I put these arguments inside of parentheses? Well, that's because we might want to give an expression as an argument, and we want to capture that possibility as well. So let's see if it compiles now. It does. Alright. Do you think it works? No! It's seg faulting. Okay, let's see what it says. strlen. Why strlen? Maybe it calls my string length function strlen. Probably so. But why does it pass int? That's a bit weird. And why does it crash? So we malloc with 0. We do a string length. So are we still inside of that function? The constructor function? Make dynamic. We allocate with 0. We do this and this. Is it the memory copy? We give it the type. So we're going to copy into the type field. And how does the type field look? Well, it's just an array like this. And we give the data type, which should be int. The string length of int should be 3. 3 is less than 15, so 3 bytes is what we should copy. And it returns 2 from int. That shouldn't really matter. 2 should be okay too. So did I miss something here? We have a destination, a source, and a size. The n is equal to the size. D is destination, S is source. As long as we have an n, we go on with a loop. And we increase the D. We increase the S. We are copying into the type. Maybe it has to do with null termination, perhaps. But we are zeroing out the whole thing beforehand. Let's add some debug message for now. So let's do this. So p type should be printed. Okay, let's see what it says. P type is equal to int. Okay, so that's no problem. So this is not where it crashes. Is it inside of the dyn add perhaps? If our count is more or equal to the R capacity, which it should not be. So the IDX is equal to 0. And the R data plus R entry size times 0. So P should be equal to R data. And into that we copy our entry. And the entry size. And we increase the count. Let's add some debug thing here as well. So if we see this debug 1, then we know that the add function also works. But we do not. And this time we didn't get the first one either. Did I remove that? Yes, I did, okay. So the add function, we have some problem here. Let's do this. Okay, so it's our memory copy. Let's try this. If we just comment out these lines and we try to print the empty array, what happens then? Data type is int, that's pretty nifty. Printing R, that's the name of the variable, also pretty nifty. Capacity is 10, count is 0, entry size is 4. Because one integer is 4 bytes. So it looks okay. Are we... Are we allocating too little, perhaps? Let's add some debug message. Allocated 60 bytes, 68 bytes. Because 4 times 10 is 40, and the rest of this is 28 bytes then. So we have room. And there's no problem with this memory copy. But there are obviously problems with this one. Let's just double check that we don't reach this point. And we need to put those back. Okay, so we don't come here, which is right. So what if we were to print what we are giving this function? So we are calling memory copy, and we are giving it the P we are giving it an int 8 version of the entry. And then the entry size. So what do we have here? We have the P. And the entry. And then the entry size. Alright, let's see what it says. It's segfaults before this. Okay, so this is no problem. So let's print the address instead then. Now we should get some useful information, I suppose. Okay. So we try to memory copy into this address, but we are using this argument, the integer, as an address and not a reference. Okay. No, this is not right. I guess we need to send the reference to this. Is it even possible to do something like this? I'm not sure. No. Well, I guess we need to do something like this then. Create a variable x, and we want to set x equal to this. And now I suppose we should be able to do this, right? Let's see if it accepts that. No. Okay, let's do this instead. So x is equal to 1, then we do din add, and we have our array. We'll send the reference to x. And we'll just change this like so. Okay, so now we send the right thing here. And now I believe it might just work. Look at this. So we have a variable r, which is a dynamic array with a data type of type int, capacity 10, count 5, entry size, so they are 4 bytes each. And here is a dump of them. So basically we have this is the first, this is the second, and so on and so forth. And we have added our 1, our 2, our 3, our 4, our 5. Okay, so that works, but what if we were to add more than 10 to it? Something like this. What happens then? Now we have a capacity of 40, a count of 35, and this is the first 32 bytes or so. Alright, so we have successfully created a very cool dynamic array which not only stores the data type and calculates its size, it does also print the name of the variable. Alright, so I think this is enough for one day actually. We have covered a lot of ground with the preparations, and next time we are going to continue on by creating the network sockets for the Unix domain sockets and communication with the user interface. And I hope you like this episode and this series. It's going to be a very cool and unique project when we are done. So like and subscribe and hit the bell button so you get notified when I release the next episode in this series. Thanks for watching and thanks for today.